Good morning, guys. So today we are continuing to look at the ratio of similitude, and we're going to look at two different problems to see how you can use the ratio of similitude in the fundamental theorem of similarity when you're dealing with lengths, areas, and volumes. And so let's see how these sorts of problems set up. One thing that I want you to do before starting any of these problems is write along the side length, area, volume, and around the length, go ahead and just put a box because that's going to be the one that we're going to most look for. This is our standard ratio. And for area and volume, I want you guys to put a squared by area and a cubed by volume. Now what we're going to work with in this one is ratio of similitude rather than k value. And let's just start with this first problem. So two scale models of the same car are similar to the actual car, and so therefore they are similar to one another. The smaller model is 15 centimeters in length, and the larger model is 75 centimeters in length. Now, before I even worry about these questions, I'm actually going to fill in this. If I want to know what ratio I've been given, I have to ask myself, am I talking about a length, an area, or a volume? And here I've been given a length. In fact, it directly says length. So my ratio here is 15 to 75. And if possible, I should simplify that ratio because we don't really want to be working with huge numbers, especially if we're going to be squaring and cubing these. So I know that 75 and 50 are both divisible by the number 15. So that means that I could divide both of these by 15 to get a new ratio, and that's going to give me an answer of, well, 15 divided by 15 is 1. 75 divided by 15 is 5, so I have a ratio of 1 to 5 for lengths. Now remember that just means in the smaller 1 centimeter would be 5 centimeters long in the larger. Now how does this translate then to my other two? It means that my area is going to be the squared version of the original. So I'm going to take my original 1 to 5, I'm going to square those. Let's not use a purple pen to write with the purple. Here we go. I'm going to square those. And that's going to give me my areas, which is 1 squared is 1 and 5 squared is 25. So it's going to be a ratio of 1 to 25 in terms of area. And for volume, I'm going to start, now be careful here, return to your K or to your original length when you do this. We have the original of 1 to 5, and here I'm going to cube that. You don't go to the area. Sometimes people grab this one. Be careful that you don't. And that's going to give us a final ratio of 1 cubed, which is 1, to 5 cubed, which is 125. Now, notice I haven't even started the problem. I just know that I'm working with lengths, heights, surface areas, and volumes, so that means I'm going to be using different ratios for a bunch of different things. If I have this set up, it makes it a lot easier to answer my question because at this point it's more a matter of matching. How do the heights of the models compare? Well, I don't have actual heights to work with, but I do know that any length, and height is a length, will have a ratio of 1 to 5. So that means they compare at a 1 to 5 ratio. You could also say that one is 5 times as large as the other. When it comes to surface areas, well, the key word here is area. Surface area, remember, is length times width. There's a bunch of different formulas there, but it is an area. So if I'm looking for that, the way that those two compare is 1 to 25. And if I'm looking at how the volumes of the cars compare, well, the volumes of the cars compare as 1 to 125. That means that 1 centimeter cubed in one car would be 125 centimeters cubed in the other. And by the way, this is just a matter of setting up the ratios. You can also use this as well. So for instance, if we knew that the large model had an interior that had, let's go with, 75 times 60 times 90. Let's say if it had 405,000 centimeters cubed inside. So that was what was inside of it. And I asked, what about the smaller? Well, I can solve this one using my formulas. If I'm talking about cubic centimeters on the inside of this car, I know I'm talking about volume because that's cubic. So what I can do here is I will go to my ratio of 1 over 125 for volume, and I'll make sure that my numbers match up. Notice here that your small is on top, the smaller amount, and your large is on bottom for your ratio. So when you set up your proportions, make sure that you still end up with the small on top, I don't know what that is, versus my larger, which is that 405,000. Now I can solve this equation, multiplying across to get 405,000 is equal to 125x. And I can divide then by 125 to find the volume of the smaller car. And that will give us an answer of 3,240 is equal to x. So that's how these can be used to solve a problem rather than just finding how things compare. All right, so let's make this a little bit more challenging. Keeping the same thing in mind, I'm going to start with my setup. I know that I'm looking at my lengths, my areas, and my volumes. I'm going to box my length because this is going to be the basis. It's going to be what you keep coming back to. And I'm going to write next to my area and my volume my squared and my cubed, just as a reminder that that's how those are going to get set up when I'm dealing with ratios. So now I'm going to go back to my problem. And my problem asks about two similar cups. So by the way, as soon as I see similar, this is how I know I want to write this out. One can fit 8 milliliters and another can fit 32 milliliters. And we want to find a whole bunch of different ratios, and then there's an additional question. So excuse me. So what we're going to do here is I'm going to start with figuring out what information was given to me. Aside from them being similar, I also know what they can fit in terms of milliliters. And when we're talking about what they can fit with milliliters, I'm saying how much liquid I can pour into it. And anytime you're filling a three-dimensional object, that is volume. That means that what I'm working with here is volume, and I can fill that in as an 8 to 32 ratio. And again, I don't need to write this as a fraction. Ratios are really nice to work with, so let's just leave this as 8 to 32. Can I simplify this fraction? Definitely. Will it help? Maybe, maybe not. It's okay to leave cubic ones unsimplified just because as you're taking the cubed root and the square root of things or squaring things, you're going to end up with some smaller numbers. So it's okay if the volume ones start out large. So what I know about this is that this is the same as my length cubed, right? Because we're talking about volume, which was cubed from the original. So that means that if I want to find out what the proportion is here for just my lengths, what I need to do is I need to take the cubic root of both of the numbers. So I'm going to take the cubed root of 8. So what number multiplied by itself is going to equal 8? Well, the correct answer there is 2, but if you don't know that off the top of your head, it's totally fine to just check out your cubic root by going to Math, going down to here, and selecting 8 to get your 2. And I can take the cubic root of 3 to undo that cube that was done, or 32 to undo that cube that was done here, and that's going to give me an answer of 3.175. It's okay to round a little bit. Sometimes proportions get a little bit distorted. Now, once I have this, I can then find my area proportions. And I'm going to start by just squaring each of these. So I have 2 to 3.175. Squared for both of these will give me my area proportions. I know 2 squared is just 4. And I can take my answer and simply square it on my calculator from the 3.175. And that gives me 10.0, let's just go with 079 for this one. And I have my area's proportions. One really large warning. Do not try to take the square root to find your area proportions. You always need to be working with your lengths values, which means anytime you're given a volume or an area, you need to go back to length, find what that is using either cubic or square roots, and only once you have that can you find the other missing proportion, okay? So make sure that no matter what one I give you, the first thing that you do is you try to find this length so you can fill in the other boxes. So this is nice because now I can just use this to fill in my proportions. The ratio of similitude is just the ratio of the lengths. So that's going to be 2 to 3.175. Surface area is an area. So that means it's going to be the 4 to 10.079 area. Diameter, well, diameter is the length across a circle. So that means I'm talking about a length. And that would be 2 to 3.175. So just matching these here. Area is down here again, and area is 4 to 10.079. And last but not least, what is the proportion of the volumes? Well, they already gave us that one. That's 8 to 32. And if you wanted to simplify that, you definitely could. You just don't have to. Now this leads us to our final question, and that is using these ratios. If the smaller cup has a base that's 240 inches squared, what is the area of the base of the larger cup? Well, remember that just like with lengths, all I need is proportion to solve for this. I have my smaller to my larger, or vice versa. You can flip that if you'd like. And currently I know the smaller is 240, and I know that the larger is unknown. So 240 over x. But I need another ratio that's filled in order to solve this. And since I'm dealing with the area of the base, right? Base, we're talking about area. I'm going to be using the proportion used for area over here, which is 4 for my smaller over 10.079. And again, just in case this is something that you tend to miss, I know this is smaller because 4 is smaller than the 10. So that's how you can remind yourself, okay, that actually makes sense. The larger number should be matched with the larger figure. And this way you can avoid having to figure out what is the pre-image versus what is the image. Well, now I can solve this by using cross multiplication. I've got 240 times our 10.79 is equal to 4 times x. Divide both sides by 4 and you end up with your answer, which give me just a second. 240 times 10.79 divided by 4 gives us an answer of 647.4, and we are talking about inches squared. Makes sense? We're in the second dimension. All right, so that is our final answer, and I want you guys to try out a few problems, and that will be it for today. Don't forget to keep working on your projects. I'm very excited to see the results. They've been looking pretty interesting so far from your pictures that you chose. Have a good day.